Okay, this video is for flat earthers who did not see Kell, Master Gunner's Sun Survey globe debunk videos and method, or for the flat earthers who didn't understand it. And I mean, admittingly, it's so simple. It takes some looking at and some thinking, because the globe model is kind of confusing. And for the globers, this is also for the globers who just looked at it, didn't really understand it, and or did and just kind of brush past it. Well, you need to pay attention here, because this summer we're going to be throwing these globe debunks at you, these sun surveys, and you need to be ready for it, or not, but at least understand it. I found a good way of breaking it down to put it in perspective. Okay, I know everybody understands parallel rays, but I found a perspective on how to paint this that'll apply to Kell's Sun Survey. And I think, the way I have it painted out here, I think I can pretty much show how the globe model is going to fail without even doing it. But I haven't done it, so in all honesty, I do want to do it this summer. But so these are all these lines. These are parallel lines. These three for number 2, 2, and 2. They represent parallel lines to Polaris. Polaris, Polaris, Polaris. 45 Polaris, 90 Polaris, 45 Polaris. So for this guy here, this guy right here, 45 degrees is Polaris to him. Okay, and parallel to that is this fella's 90-degree Polaris, and this guy here, his 45-degree Polaris on the other side, obviously, of Polaris. So I wrote 2, 2, and 2. So them are parallel lines, and you have to go like trillions of miles to get the stars to change even 1 degree in the globe model. And as far as the sun goes, you have to go like around 1,000,000 miles to get the sun rays to change angle 1 degree. Okay, so I'm using Polaris for simplicity's sake, and I have this. This is the brown box star, and this is the blue triangle star. We're going to keep them in the same position for simplicity's sake, which is why I use Polaris. Okay, so my point being here is that for this guy, his 90 is the brown box star, which is his 45. Okay, and this guy's 45 is Polaris, which is his 90. Okay, it works vice versa. Now, let's say if this guy with the Polaris is his zenith, his 90 degree, he could go up past the moon, as long as he doesn't change angle. Okay, as long as he keeps this orientation, he can go up, 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 up. And if he looks 45 degrees, he'll see this brown box star. So Polaris is in this position, and this position all at once. And however many people are observing it, that's how many positions it's in a globe model. So all at the same time, if this guy looks 45 degrees, has Polaris. This guy looks 45 degrees, has Polaris. This guy looks 90 degrees and has Polaris. It's going to be in all them positions all at once. So the globe has their own little issues with Polaris. They like to pick on the flat Earth about Polaris changing heights in triangulation. I'd like to point out which neither model, the sextant doesn't use the height of stars in the triangulation on either model. So in fact, let me point this out real quick. Blue Marble Science made a video about how Polaris changes, the distance to Polaris changes to like 20,000 miles if you're 2 degrees from the equator. But if you are 2 degrees from the equator in a globe model, and the sun is like already set, but we're still seeing it, then you're putting Polaris off by like a quadrillion miles, okay? So your model doesn't really have room to talk. Okay, now granted, they do have a mathematical explanation of why Polaris is in all these places at once. Okay, but that comes with consequences, and that's what we're covering here. So like I said, if this guy here with the brown box star as his 90 degrees, he can go all the way down to the middle of the earth. If he doesn't change angles, then he will have a 90-degree brown box star and a 45-degree polaris. He can go all the way to the moon. He'll have a 90-degree box star and a 45-degree polaris. Okay, same thing with this guy over here with the blue diamond or the blue triangle 90. Okay, he could go all the way down to the center of the earth and he will have a blue triangle 90. Okay, also he can go to the moon. This guy could go down to the center of the earth and have a 45-degree polaris, and this guy can go all the way to the moon and still have a 45-degree blue triangle star. Okay, no matter where they're at, as long as they don't change angles, and this is important for the perspective on Corey Kell's Sun survey box. This is very important, so remember that. You can go any height or any depth, as long as you don't change angles, is what you're going to see. So one more time. So this observer's 90 is the blue triangle and his 45 is Polaris, whereas this guy's 45 is the blue triangle and his 90 is Polaris. So it just switches. So and these lines are parallel, as well as the lines to Polaris. They're all parallel. So that brings me to this. This diagram is a representation of Master Gunner Corey Kell's Sun survey idea incorporated with my parallel rays diagram. So for the sake of explanation, I've left all these parallel lines up. And for anybody who hasn't seen his idea, I'll break it down real quick. This box represents the section of Earth to be tested. Okay, it represents 3,113 miles, which represents 1/8 of the globe. So 3,000, 3,000, 3,000, 3,000. Okay, it represents 3 hours of sun travel, which should be at 15 degrees an hour, 45 degrees. So he has found a way to do a survey to hold these parallel rays claim in check. Basically hold them accountable, because if the sun travels more than this 45 degrees, then it's going to be in the red. I think he gives 1 degree leniency for refraction and whatnot, but if it goes past 46 degrees, then their claim of a 93 million mile sun in parallel rays is null and void. Normally, if we do a sun survey like this, we're going to pick a starting point and a starting time with the sun at zenith. We're going to check it 3 hours later to test to see if it has moved 45 degrees or very close to it, which is 15 degrees an hour. What Corey's come up with is like a simple but brilliant way to put that same 3-hour observation to a test at an angle to hold the globe accountable for its claim of a big ass sun far, far away. So what I've done here is I've replaced Polaris with the sun. So, and I've got our same 3 observers. Remember our same 3 observers with this guy's 45 is the same position as this guy's 90. So these parallel lines they all represent the same position. And like I said, so the sun's so far away, so technically what they'd claim is this isn't 45 degrees, it's like 45.000000038, and this ain't 90, this is like 90.000000038. So eventually these almost parallel lines 93 million miles away will meet. Okay, that's how they make that claim. Okay, one more time for the sake of drilling this home. Where I replaced Polaris with the sun, these 3 points represent one big ass sun far, far away for all 3 observers. Okay, it represents a 45 degree angle for this guy, and a 90 degree angle for this guy, and a 45 degree angle for this guy. So if these 2 guys are looking 45 degrees, they're looking right here. They're looking the same as this guy's 90 at the same time. And I'm trying to drive this point home to get it across that we could move this box anywhere within a few 100,000 miles and do this same test. You could move it out in space. You could move it down beneath the earth. As long as you keep that angle, and all you're measuring here is angles, so this parallel light can't break its own rules. It has to obey the laws defining it. So this guy's 45 is the same as this guy's 90. Now, this guy's 90 is opposite of this guy's 90, basically. If he's looking 90 degrees this way, he's looking at this guy's zenith, basically. So his horizon is this guy's zenith. His sunrise, this guy's sunrise, is this guy's zenith. So think about it like this. Okay. Think about it like this. Okay. Here's this guy's zenith, directly overhead. That means this is the section of Earth that's in sunlight. So this guy's just getting sunlight over here. He's just getting it. And all this is dark. So 90 degrees to him, 90 degrees to this guy is the same as directly overhead 90 degrees to this guy. See what I'm saying? So this sun represents the same position as that sun, and vice versa. This guy's sunrise, this guy's solar noon is this guy's sunset, because then this part of Earth would be lit up. So I'm sure you understand that. I'm trying to drill it home to make this point here. Okay, so as long as he keeps this angle, he'll have a sun directly overhead. As long as he doesn't change angles, no matter where he goes, he can go way over here. As long as he keeps that angle, this sun's the same place. This is this guy's 90. This sun is this guy's 45, and it's this guy's zenith. So we call that this guy's 180 or whatever you want to call it. But we'll call that 0. This guy's 0 is this guy's 45 is this guy's 90. That's the same position. They're all looking the same exact direction at one big ass sun far, far away. So looking at it like that, think about this test. So if he's starting off, we're angling this guy this way. So we're testing the sun from this point 3 hours to this point. And if it passes this by more than a degree, then the globe model fails. They can't get around this. But if you look at it, the sun has to travel from here all the way to there. If we're doing a regular survey, it's got to go from there to there. So we've seen that in their model, the sun pretty much on paper is in more than one position at one time because of its distance and its size. They like to use their angles right here on the ground, and they draw the analemma on the globe. But then when they try and give you examples, they try and point to angles way out in infinity or 93 million miles and try and give you a concept of an angle that's changed when it's the same angle as it is on the ground as it is, infinity miles, quadrillion miles, or a sun 93 million miles away. So I think Corey Kell, that's why I say his idea is genius, man. He's already done it. He's already done this survey, and it's failed. So basically what it's doing is, in our model, when the sun's rising, it stays low on the horizon as it's approaching us. It's, rapidly approaching us. It lingers on the horizon a little bit as it's coming toward us or going away from us. It lingers on the horizon before it sets, before, refraction does its thing in perspective. But in their model, the sun is not really there. When we first see the sun, let's say when the sun's setting, we're looking at it sitting on the horizon, but it's already set in their model. We're seeing a sun that's not really there. So that to me is pretty, this is the whole kit and caboodle I think that we're testing, is when he's conducting this survey, the question is that sun on the horizon Is it traveling towards us at a steady rate, therefore passing this 45-degree mark? Or is it like the globe model? Is it lingering there and not really there? And then as it rises above the horizon, the refraction, you know, straightens out, and then so the refraction straightens out, and then it lines up with 3 hours 45 degrees. I think in reality the sun is heading towards us at a steady rate from the point we see it, and that it's going to pass this 45-degree mark by a few degrees. But this is a consequence of their parallel rays. There's no getting around this. Now, there is getting around it. If the sun stays within its confines, then it's not a proof of anything. It's not a debunk of anything. And to be honest, I haven't done this yet, but this summer I recommend we all do this. We get together, we talk about this. This is something easily provable one way or another that we can do for cheap. And it's, there's no excuse for them. Within a half a degree or so, even a degree, I'll give them a little excuse. But if it goes past that, which I think he's, I trust this guy. I still want to test his work before I go making, too many claims. But I wanted to point out the consequences and the rules that the sun has to obey. These angles have to follow the geometry of it. So thank you.